We are on the last major section of this course. We shall start this lecture by watching another video. But due to copyright issue, I'm not at the liberty to simply upload the original clip to Coursera. Instead, I will have to direct you to the external site where the clip is posted. This video I think provides a good intro to the bizarre world of atomic and subatomic particles. So, did you get the point from the video? In case you didn't, this is the crux of the matter. You see, from the classical physics perspective, and by classical physics I'm referring to physics up to early 1900s, there is a very clear distinction between waves and particles. Waves superpose. Particles do not. We never observe two tennis balls superpose each other to form a basketball, do we? So it is pretty straightforward to determine whether a physical object should be treated as a wave or a particle. Just send the object through a double slit. If it forms interference pattern behind the slit, it is a wave, and it should be studied using Maxwell's equations of electromagnetic wave. If it does not, it is a particle, and it should be studied using Newton's law of motion. Interestingly, electrons do interfere, as shown in this experiment. Using the experimental setup shown on the right, this Japanese scientist from Hitachi Research Lab literally shot electrons through two slits and shows that electrons do form interference pattern. Every dot shown here is a result when an electron hits the detector. After many hits, the pattern shows a bright and dark fringes typical of an interference. This thus raises a question: what is the nature of electron? Is it a particle or a wave? Mind you that electron does have a mass, 9.11 times 10 to the power of negative 31 kg. If it has a mass, and it is moving, which is generally the case in free electrons, then it carries momentum. Momentum, however, is not something associated to wave, because wave does not have mass. Wave is typically characterized by quantities such as wavelength. And there is somewhat a relationship between the two quantities when things go really small. Of course, you may then ask me, how small is small? Well, there is no definite answer to this, but generally scientists agree that such phenomenon is exhibited at the scale of nanometer, that is 10 to the power of negative 9 or smaller. At such scales, a particle behaves like a particle as well as a wave. A wave-particle duality. It was Louis de Broglie, a French physicist, who first wrote down the exact mathematical formulation relating momentum and wavelength. The physical constant denoted by h that relates the two goes by the name Planck constant, named after Max Planck, a German physicist. It carries a value of 6.626 times 10 to the power of negative 34 kg meter square per second. We will see this Planck constant frequently in this chapter. So there we go, momentum is equal to Planck constant divided by wavelength, a truly remarkable equation which essentially says that particle is equal to wave. There is an interesting consequence from the dualism of wave and particle. Actually, there are many more interesting consequences, but we'll just bring this one up in this course. Remember Arboy from Lecture 2.5? It is straightforward to pinpoint the very exact location of Arboy once a coordinate system is set. And that's because particle, which clearly Arboy is belong to in classical physics sense, is distinct. It is localized. Wave, on the other hand, is not. Wave permeates the space. Thus, if somebody ever asks you, where is the wave? Your answer should be, it's everywhere. But it does make sense to us what the amplitude of the wave at a certain point is. Now, if we try to combine these two seemingly opposite traits of particle and wave, we will end up with what physicists call a wave packet, a localized wave, as some laymen would call it, but it sounds like an oxymoron to me personally. It is a wave. It is localized in the sense that we can somewhat pinpoint the location of the wave through its varying amplitude. The higher the amplitude, the higher the chance of locating the object. A traveling electron, for instance, can thus be depicted as a traveling wave packet. However, notice what I said just now. We can somewhat pinpoint the location of the wave. The keyword here is the word somewhat, because locating a wave packet carries uncertainty which is determined by the width of the wave packet. Yes, we can guess roughly where the electron is, but we cannot exactly pinpoint where it is, as it is permeating a certain region in space just like a wave. And this brings us to the famous Heisenberg uncertainty principle, named after another German physicist, Werner Heisenberg. The principle says, the position and momentum of an atomic and subatomic particle cannot be simultaneously measured with arbitrarily high precision. In other words, if we are able to measure the position of the particle very accurately, that is delta x goes very small, forming a very localized wave, then we will lose accuracy in the measurement of momentum, that is delta p goes very large. And vice versa, If you're able to measure the momentum of the particle very accurately, that is delta p goes very small, then we will lose accuracy in the measurement of position, that is delta x goes very large. The accuracy in the measurement of both quantities simultaneously is limited by the Planck constant divided by 4 pi. We started this lecture with a video clip. We shall conclude this lecture by doing the same. Enjoy the video.